So our equations of motion over there, just these equations of motion. Let's write them here, please. The first term, let's divide by cosine squared phi to get theta double dot minus 2 tan phi theta dot phi dot. The second term is ready phi double dot plus sine cosine theta dot squared equals 0. These are your equations of motion coming from mechanics, and I invite you to compare them to here. So what do you think?
It's like super easy to calculate the acceleration now.
So first of all, when you compare the two sets, how do they compare to each other? They're exactly the same, right? So this is the main point of geometric mechanics, is that what was the essence of Newtonian mechanics? What was the essence? Yeah, Newtonian mechanics is all about F equals ma, but actually this is not the essence. When people start to study how particles move, they want to study the motion of free particles first. Free particles under no external forces. So Newtonian mechanics, you all know that Newtonian mechanics is concerned with motion of particles in what?
Equilibrium.
In Euclidean space, in three-dimensional Euclidean space in particular. Here is R3, this is Newtonian mechanics. Particle moving in R3, no curvature, nothing, right? What's the essence of Newtonian mechanics? What's the main principle? A free particle, free meaning no external force, moves in a straight line. This is the main thing. This is the main point. A free particle, you throw it, it moves in a straight line. And this is exactly what we're saying here. From a pure geometric point of view. Now if your particle is not moving in three-dimensional space, give me whatever space you like. Give me any Q configuration space you like. My free particle will move on a straight line in that space. What do we mean by a straight line? Go and get your straight lines in that space. It's curves with zero accelerations. Okay? So this is the main point. Now, along with Lagrangian mechanics, Newtonian mechanics is concerned with just particles. In Lagrangian mechanics, no, I don't care. Give me 10 degrees of freedom, three systems, three particles, maybe a couple of rigid bodies and one particle, and they all have maybe 10 degrees of freedom after removing all the constraints. I have 10 degrees of freedom, they form Q space, and this Q space may be curved, I don't care, right? I have some Q space, it's not R3 anymore. And to me, the whole system, the two rigid bodies and the particle, is just as if it's a particle in the Q space, right? It's a point in the Q space. And how does it move in that Q space? Under no forces, it moves along a straight line in that space. Okay, how can I get the equations of motion? Well, we have our ways to get the equations of motion, but if you want to get them from a pure geometric point of view, here it is. How do you get your straight line? It's just related to how you differentiate along the manifold. Give me your gammas that define your differentiation along the curvy space. They completely give you the equation of motion from a pure geometric point of view. It's an elegant way of doing the equation of motion. It's not that practically useful, but when you have this generality, then the next step is relativity. This is the main concept underpinning relativity. Actually, we have some time, so you don't need to postpone it to next time. Any questions so far that our equations of motion are just geodesics? They are just straight lines along our configuration space. They're just straight lines. My particle, if it's freely rolling on the sphere, It's rolling along a straight line. Just get your straight lines and you'll immediately know your trajectories. Your trajectories are just straight lines, okay? Any questions so far? So when you have, again, when you have a satellite, an orbiting satellite, ignore just the effect of gravity. We'll talk about gravity next time, which makes things much more interesting. Ignore the effect of gravity. An orbiting satellite in no gravity. When you have a free particle, you throw a particle. When you have any system that is free, no forces, now it's just moving along a straight line in your space, whatever this space is. So when actually, this is an important thing that we need to discuss before moving to special relativity of Einstein. Okay, so the Newtonian mechanics has to do with particles moving in three-dimensional space under no forces. A free particle will move in a straight line. That's fine. Okay. And how can you describe the equation of motion of this guy? How can you write it? Well, we know that the acceleration is 0, right? That's right, but how can you write it in coordinates? There is no way to write it in coordinates. Unless your coordinate system is inertial, is fixed or moving with constant velocity. If this is the case, so here's are your x's, x1, x2, x3. If your system is inertial, is not rotating, is not accelerating, your system is inertially fixed, then it's x1 double dot equals 0 up to xn double dot equals 0. Okay? So the only way to write down your equations of motion in Newtonian mechanics for any coordinate system, it has to be an inertially coordinate system. If it's not inertially coordinate system like the spherical coordinates, no way, I cannot write it directly. You'll have to go and derive your accelerations in terms of these coordinates. I cannot tell you how to do that. Okay, there is no magic general formula for the acceleration in terms of any coordinate. Over there, yes, indeed we have. For any coordinate system, I don't care about it. It's like this. This is the equation describing your straight lines, your trajectory in coordinates. It's xk double dot plus gamma I j k xi dot xj dot is 0. This is in coordinates. Give me x's, it's like this. Give me q's, it's like that. Give me y's, it's like this. Give me theta and phi, it's exactly the same way in every coordinate. This is why we call Lagrangian mechanics is coordinate independent. I don't care. It's like Lagrange's equation. It's d by dt partial L partial your q dots minus partial L partial your q equals 0 all the way. Right? You cannot try the similar expression for Newtonian mechanics. There's not. That is coordinate independent, coordinate free. I cannot. Okay? One more thing. We know now these are our equations of motion. Actually, they correspond to what? They correspond to the set of equations for any mechanical systems. It's mass matrix times q double dot plus the Coriolis and centripetal, right? Actually, they correspond to this system after multiplying by m inverse. Okay, so if you multiply by m inverse, you get here q double dot corresponding to x double dot, and this term is exactly the same as this term, which you can use to get the gammas, by the way. Okay, if you look at it, you will find that we can get the gammas from here. I'll tell you another way, but this is a very obvious way to get the gammas. If you look here, this coefficient is negative 2 tan phi, multiply theta dot phi dot divided by 2 to get the one multiplying theta dot and phi dot and vice versa. And if you look like here, this is sine phi cosine phi multiplying theta dot square. This is the one sine phi cosine phi multiplying theta dot square. But we'll know another way. This is not the objective way. Here's the objective of this comparison. So this is indeed my total acceleration, which now on we're gonna call geometric acceleration. Okay? It's not the double dot only, it's not the centripetal only. It's very interesting to note that this term by itself does not transform well under coordinates, and we have seen that today. Actually, this term also by itself does not transform well under change of coordinates. But together, interestingly, they have a very beautiful meaning, which is the total acceleration or the geometric acceleration. Okay? So this nabla gamma dot is nothing but your total acceleration, the left-hand side of your equation from pure geometric point of view. There you go, we have 15 minutes. Actually, we don't need all this. 15 minutes is a lot, we can do a lot. We can have from next time to save time from next lecture, so we can do some more mathematics. So any questions so far? Instead of just speculative, next time we're going to talk about both. Just a glimpse of speculativity, a glimpse of generativity, and how they fall into this thing. Without this, you can see something. Without these beautiful concepts, I can write down my equations of motion very fine. I don't need to know them at all. I totally agree with you. And I highly encourage you to find a practical situation in which you want to write down your equations of motion. Don't go here, please. Okay? Obvious. But I tell you, without this concept, the generativity would not be developed. Would not have been developed at all, for sure. Okay? Without this concept. That this the generality of the concept. What's the generality of the concept? The motion of my particles move, my free particles move along straight lines in whatever space you have. Okay? Yusharus told me at the beginning another definition for a straight line. So we're still with a straight line, but another beautiful definition. And we'll see how the two definitions, they collapse in each other. And they gave us already this time. Next time they give us another thing, which is exactly equivalent and from which Newton got, or Einstein got the general relativity. What is the definition of a straight line? The other definition. So first definition is a curve with zero acceleration, and we fully exploited that to get here. What's the second definition?
Shortest path?
What?
Shortest path?
Yes, exactly. Like Joseph and Charus were saying, a straight line. Yes, it is a curve with zero acceleration, but it's also the shortest path between 2 points. Shortest path, shortest what? Shortest, we need to measure distances or length of curves and get the curve of the minimum distance, right? The minimum length. So I have 2 points, here is your manifold. I have 2 points, I can connect these 2 points by infinitely many curves. The straight line among the 2 points is the one that connects the 2 points with minimum length, right? And again, we don't take anything for granted once we start with differential geometry. When we say shortest length, how to compute length, right? How to compute how are you going to measure the length? So actually measuring the length has a long way. Here I'm in a gradient space. Measuring the length has to do with measuring, we're doing dot product. Okay? So dot product or inner product. Do you have any question before going into this math? It's interesting math, but do you have any question first before going here? Any question about the concept that we discussed? Or how to compute things? Any question? Okay, so we're going to take a new concept here. So we're going to define maybe our last word. Hopefully next time, I don't think. Maybe today. So dot product or inner product. How do you do dot product if you have V and W and Rn? How do you do dot product between V and W? Well, this is
Magnitudes and cos.
so we do V, W, right? We denote it by this bracket is equal to summation J1 to N Vj Wj, right? Okay, and actually if I have a matrix, if A is a symmetric, positive, definite matrix. Then I can define the dot product or the inner product with respect to this matrix. How? Well, V and W now will be defined as summation I1 to N, J1 to N, Aij, Vi, Wj. Or it's the V transpose as a row, A as a matrix times W as a column. Okay? So the dot product is a mathematical operation, takes from you two vectors and gives you what? Numbers, scale. Very good. So this is the dot product. It represents what in geometry? This number represents the angle, right? If you divide it by the magnitude of the two things, you get cosine the angle between the two vectors. So if you are in some space, some developed space, very well developed space, like Euclidean space, where you have the capability of doing dot product between vectors, then you have a means of measuring angles between vectors, okay? Because you don't have this in any space, by the way. And if I have this capability, immediately I have, this is the highest capability, by the way, because if I have this capability, I can measure length. How? Well, here is the norm. We define the norm. The norm of a vector is simply the square root of the dot product of the vector itself. You just told me that you can do dot product. You can do dot product between two vectors, then do it for the vector itself, please. You get a number squared. This gives you a means for measuring the length of that guy. So if I have a curve, how do you get the length in of the curve in Rn? How do you get the length? This is gamma is from 0t to Rn. A curve in Rn, that's fine. We're still with Rn. So how you get the length of gamma? What's the length of gamma? What is the integral? 0 to t of the norm of gamma dot. This is not n. dt. Gamma dot times dt gives you the length, which by definition here is square root of gamma dot with itself. Okay? Any questions so far? You have the ability to do inner product, you immediately have the ability to measure length of things. Any question? Okay, so now we are in our manifold. N-dimensional manifold.